Okay, congrats everyone, kind of made it. Today's the last lecture, and as I always tell my classes, I've made every single 8 a.m. lecture this semester, so I'm kind of pleased with myself. Okay, let's get the review out of the way. So we go back to the beginning, like when you were bright-eyed and first day of class. While we didn't actually drop a cat out of a plane, the idea in the very beginning was to discuss how to describe motion, right? Like that's where we started with motion along a straight line, right? So we defined position, change in position as displacement, rate of change of displacement as velocity, rate of change of velocity as acceleration, right? So those were your main topics, right, at the beginning, and all of them describe motion of a particle, right? So the change in an object's location or position is called its displacement. The rate at which that displacement changes is called its velocity, right? And velocity is related to what you guys call speed, right? Speed is always the magnitude of velocity. We learned that velocity is a vector quantity. Speed is scalar, right? Velocity is how fast something is moving and in what direction it's moving. Speed is just how fast it's moving, right? So part of physics, like at the very beginning, was differentiating between quantities that are vectors and scalars, right? So, and how they add. Scalar numbers are just scalar quantities. Mass is a scalar. If I have a 10 kg mass and a 20 kg mass, and I put them together, I get 30 kgs, right? But displacement is not a scalar, right? So a displacement of 2 meters and a displacement of 3 meters doesn't have to add up to 5. It depends on how they're oriented with respect to each other. If you go 2 meters that way and 3 meters that way, then yes, you went 5 meters that way, right? But 2 that way and 3 this way means you went 1 meter this way, right? So remember that, right? Vectors and scalars, the difference was how they add, right? And as we move on, we dealt with vectors in 2 dimensions. But before we got there, a couple of things. Free fall would be motion in the y-axis, right, or the vertical axis. And in the vertical axis, at least near the surface of the Earth, everything falls with the same acceleration due to gravity, right? And graphical analysis of linear motion. Big words describing just putting stuff on a graph, right? The slope of a position versus time graph is the velocity. The slope of a velocity versus time graph is the acceleration. Okay? These were your kinematic equations. And a lot of the beginning, like the first 2-3 weeks, remember, was about algorithms. It was developing how to solve a word problem. Right? So when you see a word problem, your first step is draw a diagram. Right? Your second step is make a table. List what you know, list what you do not know. Right? And then use the appropriate set of equations. Okay? Remember, the big caveat to these equations was they apply in the case where acceleration is what? Constant. Right? So all of these apply for the case where acceleration is constant. So remember, speed is distance over time does not apply when acceleration is involved. Right? If acceleration is involved, you have to use these. Okay? This is, well, showing you that in the absence of air resistance, everything close to the surface of the Earth falls with the same acceleration due to gravity. Okay, so the idea here is always think of displacement, velocity, and acceleration, but they're different, right? Velocity is the speed with which something is moving in a certain direction. Acceleration is the rate at which that velocity is changing, right? One of the biggest things in physics is separating velocity and acceleration, right? And always remember this, right? I told you this at the very beginning, so let's recap. V and A are both vectors, right? So velocity and acceleration are vectors. If V and A point in the same direction, right, the object is speeding up. Okay? If V and A point in opposite directions, the object is slowing down. If V and A are perpendicular to each other, the object is turning. Okay? So how velocity and acceleration orient with respect to each other determines what happens to the object. Does this make any sense? Right? So remember, decoupling. V and A are not the same thing. A is the rate at which V is changing. Okay? If v is not changing, a is how much? 0, right? Something isn't changing, its rate of change is 0. Okay. After that, we got to projectile motion. And the puppy obviously didn't get the memo. Okay, so the way you solve a projectile motion problem, if you remember, is decouple x-axis and y-axis, right? And for a projectile, you know the accelerations in each axis, right? For any projectile, the acceleration in the x-axis is 0, right? It's moving at a constant velocity in the x-axis, right? And in the y-axis, its acceleration is little g downwards, right? It's basically in free fall, right? So any projectile can be treated as a combination of two linear one-dimensional motions, right? One is walking in a straight line, right? That's the horizontal axis, and the other is going up and down, right? That's the vertical axis. You put those together and you get a projectile. Right? The important thing with a projectile motion kind of problem is to separate quantities, the vector quantities in the x-axis from the vector quantities in the y-axis, right? The only thing in common, of course, is what's the same for both x and y in a projectile? Time, right? The amount of time it's moving is the same for both the x-axis and the y-axis. And which axis determines how long the projectile is in the air? The y-axis, right? So it's essentially like how high it goes that determines how far it travels, right? Okay. So let's do a quick separation problem. Okay, so over here, all I'm going to do is set it up, right? You have a ball kicked with a certain initial velocity, and that initial velocity is making an angle to the x-axis of 55 degrees, right? And you're asked to draw a diagram, label all quantities, find how long it's in the air, and how far does it travel, right? I'm not going to do the whole problem, but let's set up the whole thing. So that is my initial velocity. If I launch it that way, that is the trajectory of the projectile, right? So this is my y-axis, this is my x-axis. Notice I've taken upwards positive, right, and going that way positive. Okay, now separate x-axis, y-axis, right? I'm just making a table, and this table I can literally make in any 2D problem without even thinking of the problem, right? Let's list the quantities: initial x position, final x position, initial x velocity, final x velocity, acceleration in the x, time, right? Same thing here, y initial, y final, initial y velocity, final y velocity, ay, right? Okay, that's my first step. Okay, diagram, table. Now look at the diagram and the question and figure out what one knows and what one doesn't know. Okay? So, this question gives me v is 15 meters per second. It gives me theta, this angle, is 55 degrees. Right? So if I consider my velocity vector, right, and this is my initial velocity vector, it has an x component, which is its projection onto the x-axis, and it has a y component, which is its projection onto the y-axis. Right? Remember how you take components? Isn't this fun? I can always see what I'm doing. Is it? There we go. Okay, so this guy is the x component. This angle is theta. So it's adjacent, so it's cosine. Right? This guy is opposite, so it's sine. Right? So this tells us that the initial x velocity is v0 cosine theta, and the initial y velocity is v0 sine theta. Everyone with me so far? Okay, now fill up your table. So my initial x position is 0. My initial y position is 0. My final y position is actually 0. I know it. I do not know my final x position. Right? I'm asked for how far it goes. That is the final x position. My initial velocity in the x-axis is v0 cosine theta. My initial velocity in the y-axis is v0 sine theta. My final velocity in the x-axis and my final velocities in the y-axis depend, of course, on the accelerations. The acceleration in the x for any projectile is 0. The acceleration in the y is g downwards. I took upwards positive, right? So acceleration in the y is minus g. Everyone with me so far? Okay, I'm going a lot faster, obviously, because we've done this before. If acceleration in the x is 0, this can't change. Right? That's what this means. Acceleration being 0 in the x-axis means velocity in the x-axis is constant. Right? So this guy is the same as it was in the beginning. Doesn't change. Right? This guy is the negative of what it was in the beginning, because how fast you throw it up, right? It's moving the same speed when it comes back down, just in the opposite direction. Right? So the direction makes it a minus. Okay? So that fills up the table. Solve for this and solve for this. Right? And the way you do this is you know that time comes from the y-axis. So treat this as a one-dimensional problem and solve for t. Right? Then treat this as a one-dimensional problem. You know t, find x. Right? So always separate. Right? And do not mix and match. Acceleration in the x-axis does nothing to velocity in the y-axis. Okay? Right. All that fun math, and that's literally all it was. It was, the beginning was just about getting you guys the tools to solve physics problems, right? The word problems. And then things got interesting. Well, actually, after this, things got interesting. This is the acceleration involved in moving in a circle, right? So acceleration is change in velocity over change in time, right? When something is speeding up or slowing down, it's pretty easy to calculate delta v over delta t, right? There is a change in velocity and there is a change in time, right? So divide one by the other, you get a, right? But the acceleration involved in turning doesn't involve a change in the magnitude of velocity. Right? So there is no delta v in terms of, like, it can turn at a constant speed. Right? So it's hard to think of a delta v in that sense, but there is a change in velocity. There's a change in the direction of its velocity. Right? That's what turning is. Right? And anything that turns, you can think of it as moving in an arc. Right? A turn is movement in an arc. Right? So there is some radius to that arc. Right? And in order to turn in an arc of radius r, with a speed v, you need an acceleration of v squared over r. Okay? And all that's telling you is, if you want to turn faster, right, you need more acceleration. It goes directly as v squared. If the turn is sharp, that means r is small. Right? It's a sharp bend, so you need more acceleration. Right? A long r implies a slow curve. Right? Less acceleration is required. Okay, so as I said in the beginning, the first part kind of does sound like a driving lesson. Okay, then things get interesting. Inclined planes. Now, Newton's laws, right? Newton's laws of motion. So the idea of physics, and this is kind of where we really started physics. Okay, the idea of physics is you have laws which are essentially axioms. Okay, they're observed to be true. Okay, and based on those laws, you make up theories, and then from those theories, you make up predictions. Once you have predictions, you have observations, and then you go back and modify the theory. Right? That's the general scientific process. Now, Newton's laws of motion, which apply to almost all your daily interactions. Right? You have three laws. The first law is the law of inertia. Right? Any object in motion along the straight line, so any object moving at a constant velocity, right, tends to move at a constant velocity unless acted upon by an external force. Right? So what that's telling you is, in order to change velocity, you need a force. Okay? A force is a push or a pull. So what does force actually cause? Does force cause velocity? No. Force causes acceleration. Right? And that's the second law. That the net force acting on an object of mass m, right, is mass times the acceleration. So if I have some net force acting on an object of some mass m, and I want to know the acceleration of that mass m, I divide that net force by that mass. Right? And what that's telling you, of course, is the same forces applied on different masses produce different accelerations. Right? So if I push a little kid and I push a big kid with the same amount of force, the little kid accelerates more. I do not go around pushing little kids. Okay? But just as an example. Okay? The third law, of course, is every action has an equal and opposite reaction. Right? And that law is dealing with forces that act on different objects. Right? The action-reaction forces will never act on the same object. Okay? They must act on different objects. Right? When one object exerts a force on another object, that object exerts an equal and opposite force back on the first object. Right? When you push something, that thing is pushing you, right, with a force of the same magnitude. Right? The difference, of course, is the acceleration that it produces. Right? Because the same force is now acting on two different objects, you get two different accelerations. Right? The more massive object accelerates less, which should make sense, right? Do not go run into a football player, but you could, right? Both of you actually exert the same amount of force on each other, just one ends up in the hospital. Okay. After the three laws was free body diagrams, and free body diagrams are important. Okay, they do not have to be artistic, right? Generally, they're just blocks, and I was drawing blocks for everything. The important thing on a free body diagram is you put the forces that are acting on an object, right? Not the forces that are exerted by the object, right? So the free body diagram of an object isolates all the forces that act on an object, right? And the reason to do that is because Newton's second law is sum of forces is ma, right? The net force on a system is mass times acceleration, right? And force is a vector. You need a free body diagram to see how the forces acting on a system are oriented with respect to each other so that you can add forces like vectors. Right? And when you get a net force, that is mass times acceleration. Okay? Then we dealt with friction. Friction is a force involved when two objects are in contact with each other. Right? So there are two basic kinds of friction, static and kinetic. If the two surfaces are sliding with respect to each other, it is kinetic friction. If the two surfaces are at rest with respect to each other, it is static friction. Okay? And friction is, the force of friction is some coefficient of friction times the normal force. Right? So the normal force is a reaction force. It's a measure of how hard two surfaces push against each other. Right? The harder the surfaces push against each other, the more friction you have. Right? Like when you want to warm your hands up, you push them together and rub, so you get friction. Right? As opposed to just lightly brushing them. Okay. After that, somewhere around the halfway point, we started discussing work and energy. And work and energy are two of the more important topics that we covered this semester. Okay? First off, work. Work is the ability to make something move. Okay, so we defined it as F d cosine theta, where F is the force, d is the distance moved, and theta is the angle between that force and that distance. Right? But just conceptually, work is the ability to make something move. Okay, that's what we're defining as mechanical work. Right? And energy, right, that weird little quantity which is so abstract it's hard to define. In terms of physics, it's defined as the ability to do work. Right? So something has energy means it has the ability to do work. Work is the ability to move something. Right? So energy is the ability, possession of the object to do some work as it moves something else. This making sense? Both of them are measured in joules. Right? And they are scalars. Energy and work are scalar quantities. There is no direction associated with it. Okay? So if we're talking about adding up works done by different forces, we do not worry about directions. Right? It's a nice scalar system. Then we came to what we call the work energy principle, right? And that depends on us describing or defining the energy involved in a moving object, right? Any moving object of mass m with some speed v has the ability to bump into something else and make it move, right? So it has the ability to do work, right? How much ability it has is 1/2 mv squared, right? The more massive it is, the more ability it has. The faster it's moving, the more ability it has, right? So the kinetic energy of an object of mass m moving with speed v is 1/2 mv squared, right? No directions. It can be moving in any direction it chooses, right? It has that much energy. Everyone with me? Okay. The net work done on a system is the change in the kinetic energy of that system. That is the work energy principle, right? So if you have net work done on a system, you are changing the kinetic energy of the system, right? If you have no net work done on a system, its kinetic energy cannot change. Does this make sense? Now, zero net work does not imply that no forces do work on the system. No. Okay, individual forces can still do work on the system. Okay, net work will be 0 if the net force is 0. And then after that we went to describing potential energy. So apart from the energy associated with motion, there is the energy which is associated with configuration, right? The energy stored in a ball that I'm going to drop from the top of Foxhole, right? That is gravitational potential energy. Just holding it there, like on top, right, means I've stored energy in the system, because when I let it go, it will go down, right? On its way down, it can hit something and move it out of the way, so it can do work, right? So I've stored energy in the system as potential energy. Okay, the two kinds of potential energy we covered this semester were gravitational potential energy, right, which comes about from changes in height, and elastic potential energy, 1/2 kx squared, the energy stored in a spring. Okay, both of which come about because the forces involved are what we call conservative forces, right? So whenever you work against a conservative force like gravity or Hooke's law forces, right, that work is stored in the system as potential energy, right? So what that means is lifting this coffee cup from the ground to the top of the table, I did work against gravity, right? That work is now stored in this system as mgh, right, as potential energy. This making sense? Right? Because the work I did was against gravity, and gravity is a conservative force, right? As I lifted it up, there was air resistance, right? I did work against air resistance, but that work is not stored in this system as potential energy, right? That's a dissipative, non-conservative force, right? So that work is lost from the system. Everyone with me? So when you have only conservative forces acting on a system, right? So if you can neglect friction, for example, then you can conserve the total mechanical energy of the system, right? Its potential energy plus its kinetic energy must stay fixed. So if I toss a ball up and I neglect friction, initially when it's tossed, it is all kinetic, right? At the way up at the top of its motion, all potential, right, comes back down, all kinetic again, right? And at every single point in its motion, the total energy is the same, right? So as it's going up, its kinetic energy is decreasing and its potential energy is increasing. And its way back down, potential energy is decreasing, kinetic energy is increasing, such that their total stays the same. Okay? And that is basically conservation. After that, we went to conservation of momentum. Well, first we defined momentum. Momentum is a vector. It is m times v, right? So you can think of it as a measure of the amount of motion in a system. Okay? Momentum is conserved for a system, right, if there is no external force acting on the system, right? So we use momentum conservation a lot in collisions, but remember, because it's conserved only when there is no external force acting on a system, I have to be careful about defining systems, right? So two objects colliding, this would be exam 2, two objects colliding, right? When they collide, is the momentum of an individual object conserved? No, right? A car hits a truck. The car's momentum must change, right? What is conserved, of course, when the car hits the truck is the total momentum of the car plus truck, right? So whatever momentum the truck lost, the car gained. Whatever momentum the car lost, the truck gained, such that the total stays the same. Does this make sense? Because there's no force external to the car plus truck system, right? So I can conserve momentum for a car plus truck system. So when you see momentum conservation, remember, conserve momentum across the entire system, all colliding objects. Right. After that was gravitation, which is another of Newton's laws, not one of the three laws of motion, but Newton's law of gravitation, right? Which was G m1 m2 over r squared is the force of gravitational attraction between two objects of mass m1 and m2. After this, we went to rotation. And the way we did rotation is to separate it from what we've covered so far, which was translation. Right? Translation was moving an object from point A to point B. Rotation is rotating an object in a given position. Right? You can combine the two motions, as in a wheel moving, rotates and moves like translates. Okay? The idea here was to define the same kind of quantities for translational motion, now define them for rotational motion. Right? So we had displacement translationally, you now have angular displacement, change in angle as something rotates. Right? Angular velocity, how fast it rotates, omega. Right? Angular acceleration, is there any change in how fast it's rotating? Delta omega over delta t, alpha. Right? After that was, well actually, there is energy associated with rotation. Right? Just like there is energy associated with translation. Translational kinetic energy is 1/2 mv squared. A rotating object also has energy. Right? Like when I do this, my arm is rotating. Right? If something was here, boom. Right? It has the ability to do work. Correct? So this kind of energy is rotational kinetic energy. Right? And rotational kinetic energy was 1I omega squared. I being the moment of inertia. Right? A measure of the rotational inertia of the system. Okay? And I depends on how far mass is from the axis of rotation. Right? The further the mass is distributed from the axis of rotation, the higher the rotational inertia. And then was elasticity, stress and strain. Stress and strain, stress is what you do to an object, strain is the response of the object to an applied stress, and the moduli, Young's modulus, bulk modulus, and shear modulus, describe how different materials respond to a given stress. And then the goals. Okay, so the idea after that, like we've now covered rotation and stress and strain, so now we're talking about actual objects, right, instead of point particles. And one motion that we need to consider is oscillations, right? Moving back and forth. And we cannot treat this kind of motion as we did in the beginning, simply because for this kind of motion, acceleration is not constant, right? This kind of motion obeys Hooke's law, F is minus kx. So the force depends on the displacement. Right? If the force depends on the displacement, that means different forces are felt by the object at different locations. So the acceleration cannot be constant. The acceleration cannot be constant, I cannot use kinematics. Right? I have to use energy conservation and come up with expressions for how fast an oscillation occurs. That's the time period. Number of oscillations in a given amount of time is 1 over the time period, that's the frequency of the oscillation. The amplitude of the oscillation is how far it's moved from equilibrium, and that is related to the energy in that oscillation. Okay? So that is, if you were to plot position versus time for an oscillating object, you will get what we call a sinusoidal motion. Right? And this is showing you that any SHM, like simple harmonic motion, can be thought of as just one component of circular motion. Okay, after all of that, right, and we went into waves. Waves are disturbances in space and time that propagate energy from one place to another. Right? We did mechanical waves, and you guys should know how to draw standing waves. Right? The harmonics and their like which harmonics are which, what is a harmonic, the relation between speed, frequency, and wavelength, what does speed depend on, etc. Okay, after all of that, two topics were left at the very end, one of which was fluids. And as far as fluids is concerned, we didn't too much about fluids at rest, okay? Except, of course, that pressure varies with depth, okay, in a fluid. And then we got to moving fluids because they're a little more interesting than stationary fluids. And over here, the important stuff was equation of continuity, right, which is basically saying that the same volume per unit time of fluid must move through some channel, right? So if you squeeze the channel, the thing needs to move faster, right, for the same volume to move through. So that product of A times V, which we call the volume flow rate, stays constant. Okay? And the other one was energy conservation for moving fluids, which is what we call Bernoulli. Right? And if you think of Bernoulli, just remember high speed equals low pressure. Right? High speeds cause low pressure. So that image, which I couldn't show you when we were doing the lecture, is wind blowing across the top of a house. Right? When wind blows, like in a hurricane, across the top, it's high speed outside. So low pressure outside. Right? High pressure inside. Right? So the roof gets pushed off. Right? What would be the solution? Windows, right? Open something. Bye-bye PlayStation, but open something. Right? Equalize airflow on both sides. Right? The difference in pressure is because there's a difference in airflow speed. Right? So if you can get the air moving inside close to as fast as it's moving outside, the pressure differential is less. Okay, and finally heat. So thermo we only did conceptually, right? I expect you guys to know what is temperature. It's a measure of the average kinetic energy in a system, right? What is heat? Heat is the flow of energy from an object at a higher temperature to an object at a lower temperature, right? And how is heat transferred from one object to another? Conduction, convection, and radiation. Okay, those are your three heat transfer processes. Okay, that was a lot of physics for 30 minutes. Now, a few details. Exams. Exam is next Tuesday, 3-hour exam. Similar format to your midterm exams, just longer. More questions. And it's cumulative, so it starts at the beginning. And it's balanced, so it's not like we're focusing more on stuff at the end. It's focused equally throughout the semester. The review session is in Olson 348, 2 to 5. If you can't attend the whole thing, that's okay. Come for what you can. The review sheet will be posted, and the formula sheet for the final is already posted in Blackboard. Okay, the fun part. Do you want a job? This is for summer. If you guys are interested, I'm looking for learning assistants. Promise there will be no grading, right? The idea on a summer course is it's a smaller class size. It's General Physics 1, so it's what you guys have been studying. Smaller class size relatively, so we're looking at maybe 20, 30 people as opposed to 300. And I'm one of those people who genuinely believes that the best learning occurs from dialogue. So what I want from learning assistants is people who walk around talking to other people about the physics that they're studying. Okay, so if you're interested, and please be interested, bug me. And you can bug me next semester as well. Don't worry about this just yet. The fun part will be that I'm trying to make this more active, so the whole idea with the learning assistant is you get to work with me on making physics problems more fun. Okay, finally, clicker question. So I'm going to open the clicker question and give you course philosophy. Right, so that's the clicker question. Now for the final, I want you guys to be relaxed, study hard. You're going into the final with a class average of 90%. Right, that is excellent. That is better than I've ever seen. Okay, so whatever you've been doing for your midterms is working. right? So study the same way, if it worked, and do the same thing, essentially. Don't freak out, it's just a lot more material. The type of questions is what you've already seen. Okay? It's, just trust me, like your scores are telling you that you actually prepared this. Okay? And as a takeaway note from General Physics 1, right? It's an introductory course in physics, right? The idea is not to answer all of the questions in the universe around you, but it's to actually help you understand how to start answering those questions. Every single chapter we've done is a field in and of itself. Okay? So the idea with the introductory course is by the end of this, you should have more questions than you did when you came in. Okay? So there is a lot more to understand in this world. Right. On that note, Dr. Narayan is going to run my course eval since I can't be here. I will see you guys on Tuesday. Unless you're there for the review session, I will see you on Friday in that case. If I don't, I'll see you at the final. And happy holidays. Have fun. Yeah, just hold up for Dr. Narayan to do the review, please. You can take it.
No, it's fine. Just take a picture. Maybe someone else doing it.
And doubt it.
By the way, can you repeat the final exam date again?
The final exam date?
Yeah, the date and time.
It's, I believe, 17, 3 to 6. Check SIS.
Thank you.
They're already there in Echo.
Well, I know, but I mean by the end of the semester.
I don't control that at all.
So there's no way.
You can check with the lecture capture office, like instructional services, like IT services. Okay, they might know. Like, I don't actually have access to the videos. Yeah, I don't actually get the videos or have video files or anything. It's a recording from there and they post it. I don't actually have any control on it. Shoot me an email?
What?
Just shoot me an email. I did, it's fixed.
It's still the same today.
Shoot me another email.
Okay.
Oh, shoot. Huh?
Right?
Right. Thanks, Enrico. Oh, Razvan's running late?
I don't know. I asked one of my students to come. Okay. Can you turn on the dock cam?
Oh, it's there.